And when I think about galaxies, I like to think of galaxies as people. If you pay attention to me and you say, pay attention to my accent or my mannerisms, you can learn something about my history, my family, the food I like to eat, the language I speak. So that has been my guiding philosophy when I think about galaxies. I like to observe their shapes, their kinematics, their chemistry, because that can tell you something about their assembly history, their interaction history, and more. So galaxies lacking dark matter, what are they? How many are there? How do you find them? How do you even make them? Today, I will explain that the way to make them is with extreme collisions. So this is going to be an extreme case of how something very dramatic can really shape a galaxy. But before that, I want to just give you a quick outline. So I'll talk about galaxies lacking dark matter first, and then I'll talk about these extreme collisions in a new cosmological simulation called Firebox. Then I'll talk about some ongoing and future work. I just hired a postdoc, so I'm really excited about what he's doing. And then I'll talk about a couple of things that have to do with equity and inclusion. The first idea is called Pachamama, which is a word in Quechua that means space-time. And then I'll talk about the Astro Sequoia project. So in addition to being a scientist, I'm also a teacher, I'm also a mentor, and I'm an artist. So this is a collective artwork that I'll talk about. But before anything, I want to acknowledge that I conduct my work on indigenous land, on Tonga Gabrielino land. I have indigenous ancestry myself, Kickapoo and Apache from my father's side, and Tlaxcalteco from my mother's side. So it's really important for me to acknowledge this, to acknowledge the land, and it's really important for all of us to do that everywhere we go. So whenever you go to space, being it a meeting, be in the subway, a restaurant, or family or friend's house, always think about the energy you're bringing to that room, because your actions and your decisions will affect 7 generations. And I'll talk more about that later today. So let's get started. First, I'd like to acknowledge my co-authors. I'm working on a ton of things, but I'm really proud of this paper. So if you've heard about this before, I've given colloquia in many places, don't worry, there's going to be a quiz for you. So just to see if you were paying attention at that time, and if you didn't, you have a chance to listen to it again here. And this paper has gotten a lot of attention, including in languages I don't understand. But I'm particularly proud of the one by Scientific American, because I learned to speak English by reading things like Scientific American. And Muy Interesante is a famous Mexican, was born in Mexico. So growing up, we had Muy Interesante. So seeing my name in there, I was like, yeah, I'm really proud of that. So galaxies lacking dark matter. So I'm going to zoom in into NGC 1052. This is an intermediate sized group around 20 megaparsec away. And this is with the Hubble Space Telescope. You see that massive elliptical galaxy there. It has this satellite. This little fuzz here is called NGC 1052 DF2. And it's called DF2 because DF stands for Dragonfly, which was the instrument that observed it. And it's really faint, it's really tiny. And this was actually observed by a colleague of mine, Shani Danieli. She used the Dragonfly telescope. And something that caught her attention was that it has these globular clusters that are really weird. I'm a very visual person, so whenever I run simulations, the first thing I do is I make images, and then I get inspired. And apparently she did the same. So she was like, this is really intriguing. So I'm gonna get some time on Keck, and I'm gonna see what's going on. And the first thing she did is she measured the mass in stars. Just by looking at the stellar light, you can get an estimate of how much mass you have in stars. And it turns out this is a 10 to the 8 solar mass galaxy. So it's like a factor of 10 smaller than the LMC. But if you actually get kinematic data with something like Keck, you can measure the velocities of these globular clusters. And what you do is the following. You measure the line of sight velocities, you draw a histogram and you feed a Gaussian, and the width, that's the line of sight velocity dispersion. That can tell you something about the dynamical mass of this galaxy. So this is what she found. So this is a histogram of line of sight velocities. These are the galaxies in the group. And the shaded histogram refers to the globular clusters in this satellite galaxy. Now you would expect that a galaxy like this should have a velocity dispersion of around 30 kilometers per second. Because if you take a low mass galaxy, the smaller the mass, the more dark matter dominated it becomes. So the expectation is once you go into the low mass regime, you should be more dark matter dominated. So a galaxy with this stellar mass should have a lot of dark matter, and the stars and the globular clusters should be moving very quickly because you have this deep potential law. But when you actually measure it, you find that it's actually much lower. It's only 8 kilometers per second. You would expect these globular clusters to be moving quickly, and they're moving slowly. What's going on? And you can do a simple calculation, like you can see that the line of sight velocity dispersion, if you know the size of the galaxy, is R half, and you measure the line of sight velocity dispersion, you can solve for the dynamical mass. Do a bunch of math, and she found that the dynamical mass you measure with the motions of globular clusters is consistent with the stellar mass that you measure by looking at the stellar light. In other words, there is no room for dark matter. That's kind of weird, right? She was not expecting this. And then the next year, so this was 2018, in 2019, they found another one, DF4. So I'm just going to call them DF2 and DF4. And they're really intriguing and weird. And these galaxies are satellites in a group. So you have this massive elliptical. This has around 10 to the 11 solar masses. And these two, both of them have around 10 to the 8 solar masses. And this really put a lot of crisis in the field. People were panicking. Well, I wouldn't say panicking, but there was a lot of contention. Observers were like, no, you gotta be wrong. Maybe this thing is actually not that far away. And maybe that's messing up with your measurements. There was a group in Tenerife who they used telescopes in the Canary Islands and re-observed these things. And then Shani got like 90 orbits on Hubble and showed that actually she was right all along. On the theory side, people who do like modified gravity, they were like, oh, look, a smoking gun against lambda CDM. And actually a couple of weeks ago, Pavel Krupa said, oh, this is also like evidence against CDM. I'm like, no, it's not. And, but no shade to Pavel. And then other people were like, yeah, maybe CDM is right, but we need to change. Maybe it's not cold, maybe it's self-interacting. So people were playing with simulations with self-interacting dark matter. Now, people like me who run simulations with lambda CDM, every group in the world tried to find them in their simulations. And nobody succeeded until we came along. So let me tell you about that. So the question is, can we explain this with simulations? And we do. So this video is this is a gas distribution from Firebox. Firebox is a cosmological simulation with FIRE. Some of you might hear of FIRE. FIRE stands for feedback in realistic environments. And the nice thing about FIRE is that we treat star formation, quote unquote, self-consistently. We're able to resolve the multi-phase turbulent structure of the ISM, and star formation is regulated by feedback. But usually in FIRE, what we do is we select a handful of galaxies from a low resolution simulation, and then we do zoom ins and we study those. Firebox is the first time we simulate the entire simulation at really high resolution. And the nice thing about Firebox is that you can find extreme cases that you wouldn't find if you focus on hand-picked systems. So what do we find? What I'm showing you here is the mass in dark matter versus the mass in stars. I am focusing on low mass galaxies, everything below 10 to the 9 solar masses. And in the observations, you focus on this R half, which is the radius containing half of the stellar light. So everything I'm showing you here is within R half of the mass. I'm not showing you all the dark matter in the satellites or in the centrals. I'm showing you the dark matter that you find within the radius containing 50% of the stars, right? And this is color-coded by the fraction of mass in dark matter. If the symbols are really pink, it means that you're very dark matter dominated. But if the symbols are kind of turquoise, that means that you're dark matter deficient. Now, let me add some lines here to guide the eye. So I can add some lines like this. So like this is a one-to-one line. What does that mean? It means that if you have a galaxy that doesn't have any gas, it only has stars and dark matter. If that galaxy is on this line, it means that half of the mass is in dark matter and the other half is in stars. So which means that we can split this plane into two regimes, the dark matter dominated galaxies and the dark matter deficient galaxies. If I include DF2 and DF4, they will be around here. They're around 10 to the 8. And now I'm only including central galaxies like the Milky Way or things that dominate their halo. But the moment you include satellites, this is what you find. So relative to central satellites, there is more scatter and things tend to go down. And that's because when I become a satellite, I start losing matter because of tidal fields or ramp pressure stripping. I start losing dark matter. I start losing stars. So let's say this one here, if you track it back in time, it used to be on that relation. And then it went down because it lost dark matter. And it went to the left because it lost stars. So most satellites, they do that path from there to here. But there are a few down here that are actually in the dark matter deficient side. So we found 7 of them. I gave them really cool names like wolf, wild potato paint, long hair, bird blue, and deer. Sounds kind of random now, but it's not. So I really debated when I found these 7 galaxies. I asked my colleagues in the collaboration, hey, I found these 7 galaxies, what should we name them? I live in Southern California, and people were like, bro, we have the 7 characters from Disney. And so I've been humbly telling the community that we shouldn't use the term dwarf when we describe low mass galaxies, because it denigrates people with dwarfism. And also it's, if I use the term low mass galaxies because I also think it's more scientifically accurate. So I'm not gonna push you, but I humbly invite you to try to use the term low mass galaxy. I think it's more inclusive. So not 7 dwarfs. I thought about the 7 sisters in Greek mythology. I'm not a woman, so I was like, it's not really my place. I have indigenous ancestry. A good friend of mine is Cherokee, and he told me about the 7 clans. And these 7 clans have different cultures, they have different cuisines, they have different histories, different personalities. And the 7 dark matter deficient galaxies that I found also have their own personalities and histories. Now you see this 7 number is coming up, right? So it turns out that in many indigenous countries, cultures like the Cherokee and the Comanche, 7 is a really important number. When you live your life, if you're lucky, you will interact with 7 generations, your great-grandparents, grandparents, parents, and if you decide to have children, it will be your children, grandchildren, great-grandchildren. Or even if, let's say you're a college student, there are 4 years in college, so you interact with seniors, juniors, sophomores, and then you become a senior and you interact with everybody else. But kind of like the idea is every decision you make, if you decide to be a jerk, or if you decide to be selfish, or if you decide to bully someone, that's not just going to impact the person you're bullying, it's going to impact 7 generations. So that we have to do things responsibly. So let me introduce you to the 7 Cherokee galaxies in Firebox. Well, I should say that before I do that, so I consulted with my friend and he consulted with the elders of the tribe. So I named them with permission. I really want to avoid cultural appropriation because even though I have indigenous ancestry, I'm not Cherokee. So this is Wolf. It's really hard to see this little guy here. This is a mock stellar image using a Hubble Space Telescope kind of synthetic maps, but this is a simulation. And in the simulation, you can look at the dark matter distribution and you see that there is no subhalo associated with this satellite. Now, for many years, we have struggled with this so-called missing satellite problem, which should be called the you have too many subhalos problem. And in that problem, it's like you have more subhalos than you have satellites. This is the reverse. This is actually the missing subhalo problem, right? The quiz is coming up, so get ready. This is wild potato. Same idea. No subhalo associated with wild potato. I really like paint because it's kind of fluffy like me. A really happy galaxy. And it also doesn't have a subhalo. So here's a quiz. What do these 3 galaxies have in common? So I want you to talk to the people next to you, and let's see if we can find what these galaxies have in common. So talk to each other. All right. If you can hear me, clap once. You can hear me, clap twice. All right. So what do they have in common? Now, if you're someone like me, I'm extremely shy. If you're someone who never asks questions at colloquia, now is your chance to shine. So let's make, just get out of your comfort zone and ask a question or tell me what's going on here.
They're all next to a larger galaxy.
They're very close to a larger galaxy. Now, this is projected separation, but in 3D, they're also really close. What else?
Next to disk galaxies?
This massive neighbor looks like a disk galaxy star forming. It has dust and ice. And okay, what else?
They seem to be tidally disrupted.
They seem to be tidally disrupted. So this one and this one, they have a tail, right? So it indicates that maybe interactions are playing a role. What else? Oh.
So two of them kind of seem to have a nucleus and one don't. So that's something not in common.
Yeah. So these two, they seem to have similar morphology. This one seems more ultra diffuse. So they are not exactly identical. What else?
Maybe it's hard to tell with the projection, but are they inclined at all with respect to the plane of the galaxy?
So I guess the question is, if I take the plane of the disk, are they on some angle relative to the polar direction? I actually don't know. That's a good question to ask. Yeah. What else? I'm gonna feel blue if you don't. Yes.
There don't seem to be other little guys around.
They are the only satellite around. Yeah, that's a good point. That's something to keep in mind. What else? I'm feeling bluer and bluer. I'm not getting redder. Come on, giving it away. The big guy is blue, and these ones are not. They are probably not, don't have any gas, they're not making any stars. And what else? There is an obvious one. What is this talk about? They're lacking dark matter. Yes.
They're all faint.
They are so all faint, and also they are like, they have similar sizes around, right? All right, so you passed. Now these are 3 out of the 7. So the next one is long hair. I love this one because I have long hair. This one is 400 kiloparsec, not megaparsec, 400 kiloparsec away from the center. But if you go back in time, this is what this galaxy did. It went in, it came within 3 kiloparsecs from the center. It crashed through. It kept going. It left the halo. So this is what we call backsplash galaxies. So it became its own center for a while, and now it's on its way back. If you look at the dark matter distribution, there is no subhalo associated to it. And the last 3, they are all in the same family. They're on the same halo. Blue and Bird, they came together like the LMC and the SMC. They've been dancing with each other for a while. You can see that bird has these S-shaped tidal tails. Deer is kind of fluffy. And this is also a backsplash galaxy. It also came in, it left the halo, it became a central, and now it's a satellite again. And if you look at the dark matter distribution, none of them have a subhalo associated to them. So I'm a good friends with Jenny Danieli, who found it DF2 and DF4. I sent her a picture of this on WhatsApp, and I said, hey, we need to write a paper, and we did. So keep your friends close. Became, especially observers, like they're really good friends to have. So going back to this, this is where the simulated galaxies are. And just to give you a mini review, there are 2 dark matter efficient galaxies in the real universe that have been observed, DF2 and DF4. They're in NGC 1052, which is a group around 20 megaparsec away. We find 7 dark matter efficient galaxies in Firebox. They tend to be they are satellites. They exhibit tidal features. They tend to be red. 3 of them are very close to their massive host. 1 is very far away, what we call a backsplash galaxy. 3 are in the same group. And it turns out that Wolf is the most similar one to DF2 and DF4. It has the same size, the same line of sight velocity dispersion, the same Cersich index. It's very similar. All of them is very similar. And it's actually the only one in the world of cosmological simulations that actually resembles DF2 and DF4. There is no other galaxy in the literature, in the simulation world, that resembles that. So that's I think that's a huge achievement of FIRE and that model. So before I go, what questions do you have for me? Lucia.
Yes, hi. How are halos and galaxies like found in the box? Like, I guess my worry is like if you're doing a certain cutoff of the number of particles, like how robust are these? Are they like way more than that cutoff?
Okay, so for this we use the Amiga Halo Finder, and we found that there were like 100,000 objects, but most of them were just blobs of gas inside galaxies. So what some people do in cosmological simulations, like if you look at Illustrious CNG, they say, okay, I'm gonna put a cut. If you say you have more than 20% variance in the blob, those are not galaxies, so we're gonna throw them away. And that works generally well. So I did that, and I found that the 7 galaxies that I found visually went away when I did that. So I kind of panicked, but I'm a very, I get obsessed with things. I'm very stubborn. So I'm like, no, I'm just gonna look at every halo in the simulation one by one from different points of view and different, it took me like 2 weeks with a notebook, just checking every blob and everything that was actually corrected, assigned. And then I found that I had to reinsert these galaxies in the catalog by hand, which tells you something. It tells you that we need to be careful with algorithms that blindly select things. I like to make the analogy with choosing students to go to grad school. If you focus on GPA only or GRE scores, yes, you might get some good students, but you might be missing out some really special students. It's better to be holistic. Yeah. Yes.
So I'm trying to understand. So the idea is that these small galaxies went through a bigger halo and then lost their halo in the process, like tidal stripping or something happened. But it's not the case that they never. So there was a time when they did have a subhalo, right?
Exactly.
Okay.
Yeah. So that's what I'm going to show next.
It's not the case that they are always without a halo. There was a time in their life when they had a halo.
Exactly. And that really brings the question, what is a galaxy? And usually the definition is a galaxy is something that has a dark matter halo. And I propose, well, a galaxy is something that had a dark matter halo at some point. So that's my redefinition. These things were normal gas-rich, dark matter-rich galaxies that lost stuff. Any other questions before we move on?
How much of these features, or like how much the resemblance with DF2 and DF4 would change it if you change the baryonic feedback in the simulation?
So the question is, if I were to rerun this with a slightly different feedback, would they still resemble DF2 and DF4?
Still resemble, yeah.
So that's an interesting thing that I want to do. So I want to resimulate these things at high resolution and play around with the physics models, because there is a question of there is a question of environment, nature versus nurture, right? So I think the nature would be the same, but the nurture would be the same, but the nature, the progenitor might be slightly different. So you have stronger feedback. Maybe you're going to have maybe a core profile progenitor or something like that. My guess is that if you change the feedback slightly, they are still going to be dark matter efficient, but how dark matter efficient that might change. That's my guess. Any other questions? Going one. Oh, hey.
Oh, sorry. Yeah, so I guess super small numbers of observed galaxies, but I guess you have you can calculate a volume out to which you could observe something so faint. I was wondering whether you could kind of have some estimate of how many galaxies you'd actually expect in fireworks. Like, did you do the kind of number calculation?
So I'll talk about that next, but I'll tell you right now.
Thank you.
If you look at every 10 to the 11 solar mass galaxy or above, we're talking about massive galaxies, about 30% should have a satellite that's dark matter efficient. So they're not insignificant. All right, so how do we make these things? So if we look at Wolf, we had the quiz, so we saw that maybe interactions play a role, right? You see that it has tidal features, it's really close to this one. Even if you look at the disk galaxy here, you see that the center is kind of dislodged. You have a disk and you have a decoupled disk. And it happens to be in the same direction as the galaxy. So this is indicating that maybe this thing plunged through and disturbed the disk. So what I'm showing you here is this is the stellar mass of the satellites in the simulation, and this is the stellar mass of their centrals. Again, color-coded by a fraction of the dark matter mass. You can put some lines there to guide the eye. So if you're on this line, you're in a major merger where you have the satellite and the central have the same mass. But as you go up, this will be 1 to 10, 1 to 100, and so forth. We know the mass of NGC 1052, that massive elliptical in the center of that group, really well. It's around 10 to the 11. And the F2 and the F4 would be here. And the 7 dark matter efficient galaxies we find are right there too. So one prediction we make is if we take every galaxy with at least 10 to the 11 solar masses, and we focus on satellites between 10 to the 8 and 10 to the 9, about 30% of them should have a satellite that's dark matter efficient. So I encourage observers to go and look for them. The other thing that I find is you see that they are kind of following a diagonal. So it seems like it's mass ratio that matters. It seems like one of the conditions is you should have a galaxy that is around 1,000 times more massive as your neighbor. So one condition, you need a 1 to 1,000 mass interaction, a mass ratio interaction. The other one, we predict that 30% of massive centrals should have a satellite that's dark matter efficient. So we can look at the interaction history of these objects. Here I'm showing you the distance between the satellite and the central as a function of time from infall, from the time it became a satellite to today. And as this orbit decays, you have pericentric passages. Those are indicated by these vertical lines. And the red vertical line refers to the pericentric passage with the closest approach. The gray solid line refers to the virial radius of the host. So galaxies, massive halos are not static, they're constantly growing. And the dotted line refers to 5% of that. You notice that this thing comes in, and at this point, it actually plunges within 5% of the virial radius of the host. These are extremely radial orbits. We can also look at the mass evolution. So when you become a satellite, you suffer these environmental processes and you start losing mass. And you see that the total mass is decaying. The dark matter mass is decaying very quickly. The stellar mass is actually, when it becomes a satellite, it keeps growing a little bit. It still has some fuel, but then it starts decaying. It starts getting tidal stripped. And the gas, at this interaction, it starts losing mass, and at this point, it quenches completely. It loses all of its gas, and it becomes gas-free. Now, if we look at the orbit again, you notice that at this point around here, it becomes dark matter deficient. So the purple line goes below the orange line. And that coincides more or less with the first time this galaxy plunges within 5% of the virial radius. So it looks as though that the other condition is you have to come within 5% of the virial radius to become dark matter efficient. Interactions can help you lose mass, but once you're able to probe the very central regions of the halo, you're able to become dark matter efficient. So I can summarize this in a really nice plot, which is here I'm showing you the stellar mass ratio of the satellite to the central. And here I'm showing you the minimum distance in units of the virial radius of the host. And I'm showing you all the satellites between 10 to the 8 and 10 to the 9. And this is color-coded by fraction of dark matter in mass. This is where DF2 and DF4 would be. We don't have any information about the interaction history of these galaxies because they are just sitting there. But we know their stellar mass ratios really well. The 7 dark matter efficient galaxies are down here. They occupy a really unique region of parameter space. So it kind of looks like a tree or a mushroom. You see that all stuff is up here. These guys are here. This side is really empty, and this side is really empty. And this is really telling you something about the experience of satellite galaxies. If I'm on this side here, my mass ratio is really high. It's like this would be a 1 to 10 merger. So what happens is if I am a massive satellite and I come within this distance, I will merge with the central galaxy very quickly because dynamical friction will be very efficient. However, if you're on this side, you're so tiny that the moment you interact with a massive galaxy, you will be completely disrupted very quickly. It will become a stellar stream and then be completely disrupted. But these galaxies, they choose a third path. They collide directly with the massive galaxy and they don't go away. Also, I'm indicating the numbers of pericentric passages, like this had 14, this had 9. So some of these are very persistent. Had 9 pericentric passages, it had 14. And they're still around. So before I move on, I just want to say something about what these galaxies can teach us. So I'm a person of indigenous ancestry who is giving you a talk in European language. And then I talk to my friends in another European language, Spanish, which is the language my mom taught me. I'm wearing European clothes, have a European name, Jorge Moreno, and I was assigned a European gender. But I'm an indigenous person. So it's, even though this process of colonization happened, I'm still here, I'm thriving, but my people paid a price. We had to give up some of our culture. These galaxies too, they weren't destroyed, but they had to give up their dark matter. If you're a satellite galaxy, you're usually given 2 choices. Either you assimilate with the massive galaxy, or you're completely destroyed. And these galaxies teach us that there is a third path, right? Imagine you're the only woman in the room, or the only person of color in the room, or the only Muslim in the room, or the only autistic person in the room. Sometimes you feel like forced to really assimilate and be like the others, or you will be ejected. And there is a third path. It is our collective obligation to create the conditions so that people can thrive, so that they don't have to experience things like this, right? So just to give you a mini review, there are 2 galaxies in the real universe that have been detected to be dark matter deficient. We find 7 in the simulations, which we name in honor of the Cherokee clans. To become dark matter efficient, you have to meet 2 conditions. It has to be, the stellar mass ratio has to be 1 to 1,000, and the interaction has to be extremely radial. So you have to come within 5% of the virial radius of the host. And we make a prediction that 30% of massive centrals should have a satellite that's dark matter deficient. And some of them have a lot of pericentric passages, and they still survive. So what's next? So I'm a bit obsessed with this. So my plan is to keep studying these extreme collisions. I wrote an NSF grant, so if you're on panels, please give me money. And what we want to do is we want to rerun this with genetically modified initial conditions, or just change the initial conditions by hand, or we can change the orbit by hand and do this kind of like hybrid zoom/idealized simulations and see how this changes if I change the orbit, if I change the properties of the progenitor, if I think it's important because David told me it's important. So if it's not, I blame him. I'm really interested in looking at tidal features because a way to observe them is if they have unique observable characteristics. So if you want to look for these things, maybe they have a special imprint that we can find. It could be tidal features, it could be chemical abundances or other things. So I'm really interested in that. And also changing the central massive galaxy, because let's say this galaxy has a quasar phase and it turns into an elliptical galaxy that's gas poor. Maybe that will change what the interaction does to you. Plunging into a gas-rich disk or a gas-poor spheroid might give you a different outcome. And something I really want to tackle is globular clusters. So these galaxies in the real universe, they have these bright clusters. It's really hard to resolve them in simulation. So what I want to do is the following. I want to take this interaction right before it happens, resimulate at extremely high resolution with really high cadence. And there is a method called Lagrangian hyper-refinement that Daniela Ingles-Alcazar has probably told you a lot about, where he uses that for supermassive black hole accretion. But we can actually put it on the satellite and say, hey, we're following the satellite, we're going to put some fake particle and we're going to hyper-refine the satellite and see how globular clusters emerge. So that's what I want to do next if I get funding. And the other thing I want to do is the following. So I'm lucky to have a new postdoc. He's Francisco Mercado. He's got his PhD at UC Irvine and got an NSF fellowship. And he said, hey, I want to work with you. So he's a free postdoc. And because all my life I've been thinking about environment, I was thinking maybe it's time to think about galaxies in isolation and have a control group in a way. So what he's doing is he's taking Firebox and he's finding these voids or low density environments, and we're gonna resimulate this at extremely high resolution. Like I would like to go down to like 100 solar masses in resolution. And this is in the Fire collaboration, we have this project called the Latte Project, which focuses on the Milky Way. And because we like coffee, I wanted to stick with the tradition. So this is cafecito, which means little coffee in Spanish. Think of a little Mexican coffee. Cafecito stands for Cosmological Field Simulations. And Francisco is leading this. And my goal, my 20-year plan is the following. So if you've been reading the news, you probably heard that NSF gave $15 million to the US Extremely Large Telescope program. This is kind of like, get your act together kind of money. Otherwise, I won't fund you long term. But there seems to be a path for actually building these telescopes. So my 20-year dream is to actually design my own survey and use these extremely large telescopes to find these galaxies, the ultra-faint galaxies in the field. I'm a really stubborn person, so I know I'm gonna pull it off. Just give me time. And okay, so now I guess we can segue back to the Milky Way. So I'll talk about Pachamama next. So Pachamama means the best translation is space-time. So if you talk to indigenous leaders in Otavalo, Ecuador, that's the best translation we found. Although people call it like Mother Earth or things like that, but space-time seems to be the best word. And I'll tell you what Pachamama is in a minute. So I was working with a ethnomusicologist, and we published this in Smithsonian Folkways. And the idea is that in Otavalo, Ecuador, they speak Quechua, which is similar to Quechua, and the way they celebrate the universe, so they interpret the universe, and the way they celebrate it is by dancing. So this is summer solstice, and you see lots of people dancing in spiral patterns. You can see where I'm going here. So this is, let me give you a quick, I guess, review of how you would make a Milky Way. So you have the Milky Way today, but this comes from a progenitor that was smaller maybe in the past. And then you can go back to really high redshift, and it used to be a tiny galaxy. Just like you have your parents and you have your grandparents and so forth, right? So galaxies, like people, they evolve. And the structure of the galaxy today might tell you something about this assembly history. But also galaxies have interactions. So for example, maybe a high redshift, the Milky Way's progenitor had a major merger, right? And that affected the galaxy. And maybe later on it had another merger. And if you follow those companions back in time, that one also had a progenitor and maybe had a merger in the past. So it's like me, maybe this is me now, this is me when I was a young adult and when I was a child. And I had strong interactions with people, maybe my parents, maybe my girlfriend, who is now my wife. But she also had her own story, her own parents, her own interactions. So everybody you meet, you're not just meeting that person right now, but you're meeting their entire history. Every interaction they have experienced, that's impacting who they are and how they interact with you. And those interactions they had are influenced by the people they interacted with, and each of them had their own history. So every person is like a murder tree, right? So, but now let me tell you how we explain this process in our field in galaxy evolution. If you read papers or reviews, and use a content warning, I'll use violent language. This is called the hierarchical picture of galaxy formation, where the winner is a massive galaxy. When a massive galaxy accretes smaller galaxies, we call that cannibalism. And if two galaxies are interacting with each other, we call that harassment. If you're a satellite and you fall into a bigger group, you are stripped of your stars. Your round pressure stripping also takes away your fuel. So you experience something called a strangulation. You can no longer cool down your CGM to make stars. And eventually you cannot form stars, so that's called starvation. So let's put these words together. So we have hierarchical picture, cannibalism, harassment, stripping, strangulation, and starvation. So what do you think? How does this make you feel? It's not a fuzzy, warm feeling, right? So what language is a reflection of culture. If you live in a community where sexual harassment is rampant and is not addressed, then people will have the gall to use that term, galaxy harassment, in papers because it's so normalized, right? So what can we do instead? We can look at how other people think about the universe and the language they use. So this is Pachamama, this is a celebration. They are dancing in a spiral pattern. And this is work with Jessie Vallejo. She's a Latina Mohawk scholar and an ethnomusicologist. And what they do is that when they celebrate the universe, they dance in a spiral pattern. And as they go around the spiral, they change gender. They go from very masculine to very feminine. And now in Quichua culture, presentation of gender is different from Western culture. So when you're being masculine, you have a really high, the pitch of your voice is really high, and you're very clumsy and irresponsible. And you're really bad at peeling potatoes. But if you become feminine, the pitch of your voice goes down, and you're dominant, and you are very, very organized, so you're a leader, and you're really good at peeling potatoes. They love their potatoes there. And so they dance in this spiral pattern. And also, they chose a spiral because that's how they think about time. So in cosmology or in Western culture or in Christianity, time is a straight line. But in their culture, it's a spiral because if I had given this colloquium yesterday, right now, the room wouldn't be that different. Or if I came today exactly a year from now, it wouldn't change so much, but it would change a little bit. So as you go around the spiral, everything is almost the same. So that spiral is telling you that change is slow, many things stay the same, but a few things change. Now, it's not just a single spiral, but every family has their own spiral. But sometimes, let's say my family doesn't have enough flutes and your family doesn't have enough guitars, so we swap members, we share members. I have run, with Chris's help, I've run simulations of mergers, and when you have a close interaction, those galaxies, they share baryons, they share stars, they share dark matter, right? You have these galactic bridges. And then what happens is like the different families in the village, they come together and they make a bigger spiral. And then eventually everybody goes to the city of Otavalo and they make this massive spiral. And when they talk about this process, they talk about the preservation of their culture, celebration of the universe, friendship, collective action, compassion. Those are that's the language they use. So this inspired me to propose a few changes in language. So for example, we could call it ancestral picture because it's a preservation of the ancestry of a galaxy. And we can say collectivism because when a galaxy donates its stars to a massive halo, it's actually contributing to enriching that halo. We can use maybe friendship. When I have an interaction with someone, I don't need to harass them or bully them. It's just, we can just be friends. And you can say things like sharing or transformation. That's a fine scientific word. Or preservation. You're preserving the variance, the net number of variants in the universe. Now, this is one proposal. You can use whatever words you want, but my goal is not for you to obsess with the words we use, but with the following question: why do we live in a culture where words like harassment are so normalized and such violent terms are normalized? So, and also we can ask the following question: is science really objective? And sometimes, especially if you're in a physics department, the physicists love to say that physics is objective. But you can see here that we have two descriptions that they describe the same physical process, but they use very different language. One of them is informed by a history of colonialism and patriarchy and ableism and capitalism. The other one isn't. And both of them can describe the same process, but they are informed by the dominant culture in those spaces. So to cheer you up, so in my classes, we talk a lot about justice, and sometimes it can be really draining. So something I like to do to heal is art. So I'm going to spend the last few minutes talking about the Astro Sequoia project. So sequoias take about 1,000 years to grow. If you plant a sequoia, you're not going to see its shade. You're not going to be inspired by its majesty because you're going to be dead by the time it grows. But you should plant them anyway, because it's not just about you. It's not just a utility. It's about 7 generations, right? And the same is true with everything you do. If you are kind to me or if you teach me something new, you don't necessarily do that just to get something immediately back, but because you're cultivating something that if you teach me something new, then I'm going to teach it to someone else, and then that's going to propagate. So that's the philosophy of the Astro Sequoia project. What do they do in practice? So we have an art studio next to our building. The students get together, and each student paints a leaf. On one side, they paint a galaxy, and on the other side, they write words of wisdom or words of affirmation. But now they don't do this. This is not an individual effort. This is a collective effort. So the students, they break into groups, and then they have to talk to each other because the drawings they make of the galaxy has to show the evolution of the galaxy. And the words of wisdom have to be interconnected. They don't live in a vacuum. So they do this, they build these branches. And this is a lot of fun because especially at the end of the semester, everybody's tired and stressed out. So it's a good way to relax. But this is something that happened that was really surprising. As they were collaborating in groups, I was listening to their conversations, and they were talking about galaxy evolution in very sophisticated ways. We were talking about feedback, about accretion, about turbulence, about magnetic fields, about accretion. It was wild. I felt like I was in a professional conference. And they weren't even aware that they were talking about science. It was just natural for them to do that. So this is more students, and they started building the tree. So what they did is each group had a branch, and then they assembled this little tree here. And this is what it looks like. And these are all the students. And now this tree, we do it every semester, but we don't do separate trees. We just keep building the tree. So this is like a year ago. Now the tree is like this big. But I think when I retire, it's going to be like some massive structure with a lot of wisdom and a lot of art. So yeah, so that's what I do. Thank you for your generous attention. And what questions do you have for me?
Thank you very much, Jorge. Especially, I really like your suggested alternate terms for the violent language.
Yeah.
I'm going to have to get a picture of that.
Yeah.
Keep that in mind myself.
Yeah, and there's a link to the article on my website if you want to read it.
Thank you. So, any questions?
So I think you mentioned also on the top right plot that yes, you mentioned that I think it was some percentage of it has to be the satellite has to get within some percentage of the visual radius of the massive galaxy. Is that a so it seems like is that a necessary but insufficient condition? So do you have satellites that do get so close but are not dark matter deficient?
So no, actually, so the ones that go within that threshold and survive multiple snapshots, they also have to be within this mass ratio. So if you're not, if you're outside this ratio, these ones generally don't make it that far in, and these ones merge very quickly. So they might be temporarily be there, and they just get absorbed by the massive galaxy.
Right. So if they do get in that,
so
they're going to be dark matter.
So I could argue that yes, there is only one condition, and then this could be a consequence of that. Yeah, had not seen it that way, but you're right.
Thank you.
How much
Yeah.
does environment matter? Like if it's a richer environment, there's more galaxies, and kind of Milky Way kind of system, Milky Way LC, or do you need to be in a cluster?
So I think the environmental factor that matters the most is the mass ratio between the satellite and the central. But also there is a threshold of how massive the thing has to be. So if you are below 10 to the 11, in Firebox at least, we find that you won't make a dark matter efficient galaxy. So we predict that Milky Way shouldn't have dark matter efficient satellites. If you find one, that's a challenge to our model. So I strongly encourage you to do that. And the same goes with simulations. If you have simulations on the Milky Way, look for them because maybe the mechanism is incomplete. Danny?
Nice talk, okay. So seeing as this is a dynamical problem, do you think that it could be actually more common than we expect? It's just because we're looking at the present day, we're already seeing like certain fraction of galaxies that are going through this bullet kind of dynamics. Essentially, if you rewind back in time, would you see the same situation, but we don't see them now because fully agreed? So I'm trying to say.
So I guess, so a higher redshift collisions are more common, but massive galaxies are not. So it's a competition of number of collisions versus having a massive enough central to really make the satellite dark matter efficient.
So it's not the ratio that's important. You also need the central to be quite very massive.
Yes, there is an additional condition, which is it has to be at least 10 to the 11 solar masses.
Gotcha.
Yeah.
Thank you so much, Jorge. It's always a pleasure to be in the audience for the talks.
Thank you.
I haven't kept up with the literature on ultra diffuse galaxies for a while, but I know there was that Van Dokkum Nature paper that had this collision happening with this string of dark matter galaxies formed.
That one?
I was wondering if you have an opinion on that kind of scenario and whether you've seen it happen in simulations. You probably planned this question already.
I have a lot of opinions.
Okay.
I have huge respect for Peter, but this paper is really strange. So they find these galaxies that seem to be on a line. And the first thought he had was that they are in a line in 3 dimensions, caused by a collision of 2 gas-rich low-mass galaxies. They collided and the debris made stars, but then feedback puffed those stars into galactic-sized systems, which I find, when I think about science, it's okay to have like weak assumptions, but you should only have like one of them being a weak assumption, not multiple of them working together to have an explanation. And this is, and the thing that bothered me the most about this is that like Ibata and other people, they have been talking about planes of galaxies for 50 years. So I think it would, and even in that field, there's a lot of debate. Is that really a plane? And if it's just like by chance, or is it actually, the galaxies are actually in a stable system? And the fact that that wasn't even mentioned in the paper, really, to me, that was a bit of a red flag. So I think if you see a plane of stuff in the sky, like let's say the planets, the first assumption is maybe it's a plane in projection, not a line. That's one of the big issues I have. Another one is that in their analysis, they use something called the Hopf transform to show that it's unlikely to have galaxies aligned like this. But in the analysis, they magically exclude the central galaxy. Given that we have published a paper where we show that interactions with that massive galaxy are essential. So those are two of the like 20 issues I have with that proposal. But I think if someone can show me a cosmological simulation where these things actually pop up and they resemble DF2 and DF4, I can recant my opinion. But meanwhile, it's an interesting idea, but that's it.
Do you have a suggestion for how the two galaxies do end up on the line, or is it just fake games?
I think we're just lucky that I think they came in here and they were going like this, and the other one is going like that.
Thank you.
Mm-hmm.
So I'm trying to understand this 5% inner halo radius that you need to go in to become dark matter deficient, right? How much does this connect to the halo concentration profile that you chose in your simulation?
So we didn't choose the halo profiles, they emerged from initial conditions. So this is a cosmological run. I wish we could play with those, but that they just emerge. The 5%, I think it's telling you more about the baryons themselves. So most interactions, there are baryon collisions, but here they're happening. These things are going so deep into the potential well that you're actually having these things crashing into the baryons of the central galaxy. So they're very unique kind of interactions, unlike anything else we've seen. Does that help?
Yeah, thank you.
Vida?
Very nice, thank you. You said that you like to test different physics, like in the future, to see like how it affects these satellites. I was wondering, like right now, if you look at the central galaxies, what do you see in common other than their mass, like the stellar mass? So do you have any special things in common for those?
Not really, and actually the ones we see, they are disks today, they're gas rich, whereas NGC 1052 is an elliptical galaxy. So, but that doesn't mean that it was an elliptical galaxy when the collision happened. So something we want to do is actually just include fire-through physics with AGN feedback and maybe cosmic rays, and Rachel can help us with that, and see what happens when you change the massive galaxy and how that affects the collision.
So we have time for one more question.
I was wondering, so you say it's like 30% chance that you'll get one. Is it common that you will get multiple, like you've got 3 altogether? How likely would that be?
I think to actually answer that question, I would need a bigger box. Yeah, but I mean, this was really expensive. Yeah.